Hi folks, this video we will be starting Unit 3, which will be Chapters 17, um, Carbohydrates. So we're going to start looking at more macro molecules or bigger molecules. And so this will use all of the same concepts we've been learning all semester and start applying them to much larger molecules. And this first class of molecules that we're going to discuss are carbohydrates. Um, so just a little bit of background in terms of what carbohydrates are. In terms of a biological system, like ourselves, they provide energy through the oxidation of the carbohydrates themselves. So if you remember, oxidation is loss of electrons. So this is redox chemistry. They support or supply carbon for the synthesis of cell components, cell walls, things like that. They serve to store chemical energy. So again, before they are oxidated, the energy through which that oxidation process releases is stored in them. And like we said earlier, structural element of some cells and tissues, we consider this a biological molecule. Essentially, it is a type of organic compound essential to life. And so we're going to start looking at these processes and compounds that are associated directly with a living organism and their ability to survive. So, carbohydrates are primarily, when we look at functional groups, are either going to be aldehydes or ketones that have many hydroxyl groups on them. So, a polyhydroxy, aldehyde, or ketone. Here we have an example of an aldehyde. This is the linear form or the straight chain form of ribose. The carbohydrates that we're going to discuss, we're going to kind of list them in a couple different classifications. A monosaccharide, which would be a single unit of either an aldehyde or a ketone. A disaccharide, which would be two monosaccharide units. An oligosaccharide would be something in the 3 to 10, but we can just kind of base it off of mono, di, and polysaccharide, meaning a long chain of these units. So one of the important aspects of carbohydrate chemistry that we're going to start talking about is the idea of stereochemistry. So up until this point, we've been dealing with different types of isomers. Remember, we have structural isomers, geometric isomers, all different kinds of isomers where it's either similar formula and different arrangement in space, or similar formula, same arrangement, but the 3D shape is different. And so a new stereoisomer that we're going to talk about are going to be enantiomers. That's this word here, enantiomers, which are stereoisomers that are mirror images of each other. The easiest way to say this is that an enantiomer or a pair of enantiomers are non-superimposable mirror images of themselves. Something that we're all very, very familiar with would be our hands. If you hold your hands out in front of you where the thumbs are pointing at each other, your hands are mirror images of themselves. If this was your left hand and this was your right hand, and you had a mirror here, the mirror of the left hand would be reflecting the image of the right hand. What we mean is they are non-superimposable on each other, is that I cannot lay one on top of the other and have everything line up. You cannot take your right hand and lay it on top of your left hand because the pinky and thumbs would line up instead of the thumbs and thumbs. You would have to flip your hand over, in which case it wouldn't be a superimposed image anymore. So one of the important parts of enantiomers are to be an enantiomer, we have to have what we call a chiral compound. And to have a chiral compound, we need to have at least one chiral carbon. So a chiral object or compound is something that cannot be superimposed on its mirror image, aka your hands. A chiral carbon would be, a chiral compound would be a compound that cannot do that. So your shoes, your hands, Lots of objects could be chiral, but we're going to be particularly talking about compounds. And to identify compounds as chiral, we need to have at least one chiral carbon in them. And a chiral carbon will be anything where it has 4 different groups attached to it. So right off the bat, a carbon cannot be chiral in a compound if it has a multiple bond. If a carbon has a double bond or a triple bond, that carbon cannot be chiral. It must have 4 different groups attached to it. So here are some examples when we start looking at carbohydrates and the shape of carbohydrates, where we start seeing this chirality and what that really means. So as we start going down the list, when we start with the aldehyde carbon here at the top, we see a double bond here to an oxygen. So automatically this carbon cannot be chiral. Again, this carbon up here, the aldehyde carbon, is not chiral because of the fact that it cannot have 4 different groups to it. So if we move down to this carbon, we can start seeing the 4 different groups as they're highlighted here. Carbon 3, the 4 different groups, carbon 4, and carbon 5. If we somehow had a compound where, let's say, this group and this group were identical to each other, the carbon, again, would no longer be chiral because it did not have 4 different groups attached to it. Many compounds, especially carbohydrates, will have more than one chiral carbon in them. Just kind of a rule of thumb as you start doing the math and the logic of this is the maximum number of stereoisomers that could be present is to the n, where 2 is the number of chiral carbons. So if I have 1 chiral carbon, that means I could have 2 enantiomers for it. That would be 2 to the 1. If I had 2 chiral carbons, that would be 2 to the 2, or 4 of them. So this starts getting, quite large very quickly, especially when you think about the fact that the carbon on the previous slide had 4 chiral carbons, which means there are 16 different stereoisomers of that carbohydrate. So these stereoisomers can get out of control very quickly, just in terms of the large number of them, but it is easier to keep track of it when we start looking at them in a particular way of drawing them. So we've already shown you this way of drawing it, but now we're going to talk about it in a little more detail. So here are ball and stick molecules of glyceraldehyde. And we denote we denote the stereoisomers as D and L for left-handed and right-handed chirality. And so sometimes it's very hard when we draw 3D representations with ball and stick to really understand what we're looking at, and it takes up time to do that. So we use what are called Fisher projections as a way to demonstrate 3D shapes in a flat, a flat 2D space. And so here what we show is the Fisher projection of both D and L glyceraldehyde. And what we show here is the vertical line will always be things that are either coming away from you. So in this case, right, the CHO of the aldehyde is behind, and the carbon here is what's popping out, and then again this CH2OH down here would be going back again. To the left and the right are the 2 of the 4 groups that are coming out towards us, and so the horizontal lines in a Fisher projection are the things coming out towards you. And the other important aspect of this is wherever we have a cross here in the center, this would represent a chiral carbon. So we have C, 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 OH, H, OH, H. Now, the other thing that we will start talking about is as these carbohydrates get bigger, it will be a little more important. But the last hydroxyl group in the set of hydroxyls that is furthest away from the carbonyl carbon If that is on the left-hand side, that stereoisomer is the L form. If it is on the right-hand side, it is the D form. So here's an example where we start seeing a little more complex of a carbohydrate in its Fisher projection. And we can see up here is our aldehyde. And if you look, right, if we draw a line down the center here, this would be the mirror image of itself. And when we are looking to determine which one is the D and which one is the L form of the stereoisomers, we look to the last set of OHs that are on a chiral carbon. So not this one, because this carbon is not chiral. The last set of OHs on a chiral carbon that is furthest away from the carbonyl, that's C double bond O. In this case, it would be this one and this one. If the hydroxyl group is on the right-hand side, it's the D form. If it's on the left-hand side, it's the L form. So what are some crazy, why do we need to distinguish these? One of the interesting physical properties that some enantiomers have are that they can rotate plane polarized light, but they do so in opposite directions. So one way to look at this would be if we had, light, just light from the sun or a light bulb or something like that, a source of light that comes in, light flying in every direction, and we can put it through a polarized lens. For example, even sunglasses are polarized often, which means the light that passes through the lens is all now going in the same direction. And if we were to put it through a solution of the D enantiomer, it would rotate the light one way. The L enantiomer would rotate it the opposite way. D does not always mean that it will go clockwise. L does not always mean it will go counterclockwise. Different compounds do different things. So there are other ways we name that. So an enantiomer that rotates light to the left would be lever rotary, and we give that a denotation with a negative sign. To the left would be, counterclockwise, so going negative, I guess, backwards in time, if you wanted to look at it that way. And an enantiomer that rotates light to the right would be dextrorotary, and we use a plus sign to denote this. The D and L designations do not represent dextrorotary and lever rotary. That's why we use plus and minus and not D and L. The property of rotating a polarized light is called optical activity. And again, the D does not always have to be plus and the L does not always have to be minus. It's just whatever is unique to that compound. In some instances, only the D form or only the L form exist in nature. If both the D and L forms exist in nature, very rarely do we see that the D and the L form exist within the same biological system. For example, carbohydrates, amino acids, all these things that are crucial to us existing are chiral. And humans are only capable of metabolizing the D isomer of monosaccharides. Conversely, most animals that we end up eating are only able to utilize the L isomer of the amino acid to synthesize proteins. So humans are unique in terms of a lot of other mammals that are out there, and that we metabolize D isomers unlike most mammals and other animals that utilize the L. So when we're classifying something as a monosaccharide, the first thing we need to do is figure out if it's the aldehyde or a ketone. And aldehydes we call aldoses, ketones we call ketoses. Basically for the rest of this, similar to how we did in Unit 2 where we had like an ending on the word to kind of tell us the functional group, here the ending ose, O-S-E, will help denote that we have a sugar, a carbohydrate. So depending on how many number of carbons there are in it. We could have a triose, a tetrose, a pentose, a hexose. So pretty similar to kind of how we've had naming systems in the past. So obviously every type of carbohydrate has its own unique name, but we can classify them just in general terms of what we have going on here. So this is an aldotetrose, which means this is the aldehyde form, functional group, and it's a tetrose, which means we have 1, 2, 3, 4 carbons. For an example here, we have a ketopentose. So here's the ketone form of the carbohydrates that we've been talking about, and it's a pentose because we have 1, 2, 3, 4, 5 carbons. Pretty much all, or I guess most monosaccharides are aldoses, simply because ketoses tend to be larger. Ketoses mean that we have a ketone, which means that carbonyl has to be more in towards the center of the molecule and not terminal. Most natural monosaccharides belong to the D series, as we talked about earlier, that we care about. And we also talked about how you figure out how you get the maximum number of stereo centers. And when we have these stereoisomers, they're always going to be in even numbers. So half of them would be the D, the other half would be the L. Here are just some examples as we start looking through different monosaccharides. Here we have an aldotriose, aldotetrose, so 4 carbons, pentose, 5 carbons, hexose, 6 carbons. These start being ones that you've probably heard of before, like glucose, galactose. You've probably heard of ribose before as well. Monosaccharides, carbohydrates in general, are often called sugars because they taste sweet. All carbohydrates are going to be solids at room temperature. So we have compounds that have lots of carbon and lots of hydroxyl groups. So think about this in terms of what we learned in Unit 2 about intermolecular forces, the ability to hydrogen bond. Because pretty much all of these carbohydrates have these polyhydroxyl groups on them, or have many OH groups, they're all capable of doing hydrogen bonding interactions with water, and therefore carbohydrates are very, very soluble in water. So the carbohydrates that we've talked about so far and that we've seen examples of are all in their linear form. Oftentimes in our bodies and during synthesis processes and things like that, these sugars will kind of wrap up on themselves into a cyclic form, and we have a structure that we deal with on how we draw these cyclic forms of the carbohydrates. It's really done as a convention so that everyone's on the same page, but they'll follow the same general pattern. All of the cyclic carbohydrate structures will have an ether like this in it, either in a 5-membered ring or a 6-membered ring typically, and so that oxygen will be in the back, and then the substituents around it will either be pointing up or down, depending on whether we have the D or the L form of it. So how does this cyclization occur? This is how your textbook goes about describing it. I have a few slides after this that might be a little more clear. So if we look at, starting here at carbon 1, here is the aldehyde portion of our carbohydrate. And then as we go down the list, carbons 2, 3, 4, 5, and 6, we can take a linear form of it and basically wrap it up on itself. That last hydroxyl group the last hydroxyl group that determined, like we talked about earlier, whether it was the D or L form, is the one that is going to help cyclize the compound. So that oxygen in that hydroxyl group at the end that determines D or L is also the oxygen that becomes the O in the ring of the cyclic forms of this compound or any of these carbohydrates. Lastly, when this ring is closed, depending on whether the hydroxyl group is up or the hydroxyl group is down, will determine whether this is an alpha or a beta version of the carbohydrate. The way I always like to remember this is beta goes boom, boom goes up. Not very elegant, but it gets the job done. Alpha would be the other one. So here we have different examples of glucose. We have beta D-glucose and alpha D-glucose. To help kind of get everyone through what's happening in the conversion from a Fischer structure to a Hayward structure, I have color-coded out each step of the process for D-glucose. And so here we can see our hydroxyl group, or excuse me, our aldehyde group at the top, our hydroxyl group that determines that it is the D form. And we go through and we see that we are now just going to kind of write this out long ways so that we can see what's going on. And the first step towards Haworth structure from a Fischer projection would be to take your Fischer projection carbohydrate and flip it on its side. Once you've done that, you're going to kind of curl the sideways Fischer projection so that you're starting to resemble that cyclic pattern. And then we have a rotation occur. Remember, these are all single bonds, so we have free rotation going on around the carbon bonds, allowing the OH group to get closer so that we can have a nucleophilic attack go on and basically close up the ring. And then depending on how the ring closed up, it will either cause the OH group down here, the H from here, and the O from here to either go down or up, and that this will determine whether it is beta or alpha. If you're still having a hard time visualizing that curling, here is an example that you can do in front of the mirror for yourself in terms of what is exactly happening. Pretend that this is your Fischer projection, your arm extended out, the aldehyde is down by like your armpit, and at the hand would be the CH2OH side of it. As you gently curl your arm up, that would be the same thing that is happening here. And when we do that, things that used to be on the top are now on the bottom, and things that are on the bottom are now on the top, right? As this curls around, things flip over. We have a rearrangement occur so that the O here can get closer to the carbon here. We have the attack occur, and we're able to close up the cyclization of the ring. So we will always name or number, I guess you could say, the monosaccharide in its linear form, starting with the carbonyl carbon. The alcohol group on the next to last carbon atom is added to that carbonyl group. In the case of glucose, the alcohol group on the 5-carbon adds to the aldehyde on the group on the 1-carbon, and the pyranose ring or a 6-membered ring is formed. In fructose, we're going to have, because it's a ketone, we're going to have the aldehyde group on the carbon 5 add to the ketone group on carbon 2, forming furanose rings. So those are the two most common ones that we see. The former carbonyl carbon is now a chiral carbon, and this gets a special name. We call this the anomeric carbon. And the anomeric carbon is the one that will determine whether we have the alpha or the beta anomer of that compound. Um, because anomeric carbon is still chiral in both of these cases, we end up with two stereoisomers, alpha and beta. So we've seen things like this before where we have stereoisomers that differ just in their 3D arrangement in space, whether they're up or down on the ring, but are still fully attached to everything the same way, right? The alpha and beta are still having the same bonds between carbons and other atoms. It's just whether that hydroxyl group is pointed up or pointed down. So here, to show you a furanose ring, here's fructose going through the cyclization as well. The same general process occurs where you have your sideways linear Fisher projection that rearranges in a way to cyclize and make a ring. And then again, that anomeric carbon, this carbon here, decides whether this would be alpha or beta, depending on which direction the hydroxyl group is pointing in. So some monosaccharides are easily oxidized, which would make them reducing sugars. So again, remember that redox reactions, wherever we have oxidation, a reduction has also occurred. So if something is easily oxidized, it is the thing that is doing the reducing. All monosaccharides are going to be reducing sugars. Benedict's reagents test or Benedict's test is one way where we can use a reagent to determine whether we have a reducing sugar or not. So reducing sugar plus copper will be oxidized, will oxidize the compound and produce copper oxide. So what we see going on here is we have the Benedict's reagent as a way to kind of test what's going on. And so, oops, sorry about that. What we have going on here is a precipitate will form when we are in the presence of the reducing sugar. So the OH groups on the monosaccharides can behave like alcohols and will react with acids or phosphoric acids to form esters. And this will be really important when we get to our next kind of sections where we start dealing with ATP, ADP. But remember, these alcohols will go through ester formation with acids. Technically, we can have ether formation with other alcohols present. So the 6-glucose phosphate and the 6-phosphate fructose are very, very important biologically to us. So what can happen is we can go from a monomer, a single unit of sugar, to a dimer or a trimer or a polysaccharide, right? So we can have a monosaccharide, we could have a disaccharide, a trisaccharide, or an oligosaccharide, or a polysaccharide. And this is just how many of these sugar units are all linked together. And the linkage occurs through what we call glycosidic linkage, or essentially just a hemiacetyl carbon linking to the next one. And when this happens, we end up with a carbon oxygen bond. And this bond is called a glycosidic linkage. So some important monosaccharides that we will talk about again later as we continue through would be ribose and deoxyribose. They're both pentoses and are used to synthesize RNA from DNA. Now, it's not terribly shocking by the name to see deoxyribose and ribose. Deoxyribose simply means that we have lost one of our alcohol groups, and that is about it. Now we still have ribose and deoxyribose, right? So all we've done is the only difference between these two is that the OH group on the 2 carbon is missing in the deoxy form. So as we move through these, the monomers or the monosaccharides, the disaccharides, and the polysaccharides that we discuss, these are the ones that you will need to know and commit to memory. So you should be able to draw them in both their Fisher and Haworth distinctions. So sometimes we need it in the Haworth form, which is this form right here. Sometimes we need it in the linear Fisher projection, but you should be able to do both. If we tell you D-glucose or L-furanose or something like that, that you would be able to draw it both in the linear Fisher projection as well as the Haworth structure. So glucose is the next important saccharide that we're going to talk about. Obviously, it's very nutritionally important for us, and pretty much everything we eat that is a carbohydrate is broken down into glucose for us to be able to digest and use. And lastly, right, is used as a sweetener, confection, other foods, simply because it's sweet. It's sugar, as we understand sugar to be. Galactose is also a hexose. It's very similar to glucose in its structure. However, here on the 4 carbon, we can see that the OH group is down in glucose, and in galactose it points up. It is a component of breast milk, or just like the milk in sugar, or excuse me, the sugar in milk. And is important for things like nerve tissue, the cushioning myelin around nerve tissue. Fructose is the first ketose that we're going to see. Again, it's sweet, sometimes called fruit sugar. It's present in honey with a 1-to-1 ratio of glucose, and is very, very abundant in corn syrup. So this is where we get high fructose corn syrup, simply because this compound just exists in it. So moving on from the monosaccharides, we can talk about the disaccharides. Disaccharides will be 2 monosaccharide units linked together by that glycosidic linkage that we talked about earlier. So when we are looking at this, when we're saying a dimer, a trimer, a polysaccharide, something like that, it's really coming back to how many carbons moved around when we're looking at this. So if we see here, we have the glycosidic linkage will be the ester formation that occurs. And we're going to look at it in terms of these 2 glucoses to make maltose. We have the 1 carbon hydroxyl group and the 4 carbon hydroxyl group. Those are the 2 that are going to be linked through the glycosidic linkage. We would call this a 1,4 linkage. The reason we call it alpha is because both of these are alpha, the hydroxyls were down, so we have an alpha 1,4 glycosidic linkage. We will talk more about the glycosidic linkages as we look at each disaccharide and then further on to the polysaccharides as well. So maltose is malt sugar. It's very simple in terms of just 2 units of glucose joined by that 1,4 glycosidic linkage, alpha 1,4 glycosidic linkage. This is formed when we are breaking down starch into glucose. So starch is a complex polysaccharide. And we know we need it to be as simple as possible as glucose for us to be able to digest it and utilize it. And so this is one of the kind of digestible units that we start getting on our way to glucose. It's found in germinating grains, so sprouted grains. It's a hemiacetal group. It's also a reducing sugar, and when this is broken apart and hydrolyzed, right? So if we add water across the bond here, we'll break this apart. We end up with 2 molecules of glucose. Lactose is another disaccharide that we're going to learn about. Lactose is milk sugar, um, and it is a unit of glucose, alpha D glucose, and a unit of beta D galactose linked together by what we call a beta 1,4 glycosidic linkage. So again, when we're looking at the molecule itself, the one carbon on the galactose, which is in the beta position, so it's pointed up, and the 4 from the alpha D glucose. I know you might be like, well, is it beta alpha? We're looking, because of the directionality that this is in, this is going to be a beta 1,4 glycosidic linkage. Sucrose starts to get a little more complex. This is what household sugar looks like. So whatever you put in your coffee this morning, if it was just plain sugar, looks something like this. And this is a unit of alpha D glucose and a unit of beta D fructose. So this is one of our 5-membered rings. Again, often found in plants. That's where we get cane sugar from. So either cane beets cane sugar or sugar beets is a good source of sucrose. It is not a reducing sugar, and again, when hydrolyzed, will produce an invert sugar, a mixture of equal amounts of the glucose and fructose. Again, this is just showing what's going on in terms with these disaccharides and their ability to be reducing sugars. Here we can kind of summarize the different disaccharides, what they're made of, what the linkages are, and what purpose they have. From there, we can talk about polysaccharides. So polysaccharides are going to be very, very big, very, very large, basically polymers. Could be potentially thousands of units long of whatever monosaccharides are being mixed up together. They can form thick colloidal dispersions when heated in water. This is basically, what happens when you get like starchy water and you get that kind of like foam in it. These kind of like crashing out of the solution. If you do any sort of serious cooking, you know that starch is used as a thickener, right? So if you've ever made pasta sauce, sometimes people tell you in the recipe to save some of the water that you boiled your pasta in, because that now has very starchy water, which helps thicken sauces. So starch is our first polysaccharide, and it's just a comprised polymer of many glucose units. And the starch is also fairly simple in terms of the fact that we have 2 forms of it. We have an unbranched form of it, which is just going to be kind of like strings, noodles, just straight chains, alpha 1,4 linkages the whole way down. And then we also have amylopectin, which will be our branched form of it. So again, this is just a repeat now of this alpha 1,4 linkage, making the amylose. The branched form of it is amylopectin, and it still has some strands of that alpha 1,4 linkage, making those like straight noodles. But in addition to that, we're also going to get an alpha 1,6 linkage. So basically what this allows it to do is, like, we have these strings of the 1,4 linkage, and then in amylopectin, we get an additional branching to kind of connect all those strings together. So because amylose is just a straight chain, when we start looking at it in terms of how does this big molecule all look all together, that straight chain starts to helix on itself. So it's kind of like a slinky. This straight chain is very straightforward in terms of the shape it takes on. On the other hand, we can have glycogen, which would be the animal starch version of this. And for this is where we get the 1,4 linkages as well as the 1,6 linkages. And what we end up seeing is it's very similar to amylopectin, glycogen, but it's much more highly branched. And then the last one of the polysaccharides that we're going to discuss is cellulose. And it's again a polymer of glucose. It's important as a structural polysaccharide. It's the most abundant organic compound on Earth, and it's basically what makes up plant cell walls. So, any plant in existence, cellulose helps make that up, the cell wall of that compound or that plant. It is linear like amylose, but it has a beta 1,4 glycosidic linkage. For us as humans, typically um, cellulose is not very easy to digest, and so for us, there's no real nutritional value, and it has more to do with being a source of dietary fiber. And here you can see that beta 1,4 linkage that I was talking about earlier that links the cellulose together. All right, that completes chapter 17. Please let me know if you have any questions with anything. Go work on your homework, keep up with your reading, and we will be back soon to talk about chapter 18.